all for today's session on design for cyclic loads and reliability of bearing. Now, learning objective of the today's session, describe the method of selection of bearing for a cyclic load and for a given reliability. What do you mean by cyclic load? Already we studied design against fluctuating load, you know very well. Now, we have seen how to select the bearing, rolling contact bearing from manufacturer's catalog. But sometimes what is happening, that time we have assumed load which is acting on the bearing, it remain constant during the operation or during running condition. But in actual practice, what is happening, load is going to change. Many times I have given one example of a lift. You know, in lift may have some capacity, 1000 kg, 500 kg, 600 kg. But you know, at ground floor, 3 persons inside the lift, then at second, again some gets out, some gets in. There is a variation in load which is coming on the shaft of that, and the bearing which gives the support. That means load is going to vary, and this is the case of cyclic load. That means again here, during that cycle means operation. What is happening? That bearing which is subjected for some load for some period of time, some load for some period of time, and some load some period of time. It does not remain constant. It is going to vary. And then how to select the bearing for that cyclic load condition and varying speed. Again, varying speed means, suppose, consider here, these are the 4 elements of one cycle. Here number of revolutions, suppose n, and out of this n revolution here, suppose in n1 revolution, load which is acting on the bearing is 5 kilonewton. Then in another revolution of this n, that is n2 revolution, here load is acting, suppose 6 kilonewton. Then again it is acting 3 kilonewton. Again here it is acting 4 kilonewton. So what is happening here? During this one element, having a revolution n1, having speed, suppose some rpm, how much load acting on the bearing? 5 kilonewton. Then for n2 revolution, 6. That means here one single revolution is divided into 4 elements. And if it is divided equally, you can say 20% of this n revolution, 5 kilonewton load acting on it, 25% of this revolution, 6 kilonewton load is acting. That means load is varying, and that's why name is given here cyclic load. It is going to vary. After when it completes one revolution, again it is going to happen or occur. This is one. Second case, you will find, suppose this is the diagram. In this case, you can consider this is, suppose this is total revolution or a one cycle or a one work cycle, in which you will find here during this cycle or a first one, suppose n1, load here it is suppose 6 kilonewton. Again it is going to down, it becomes 0 here, and again it is going to increase. That means variation in load in first, second. This is also another second situation. In this situation, for different elements 1, 2, 3, 4, load constant, and accordingly for different element it is going to vary, and here it is always varying one. If such a situation occurs in some of the applications, you will find load is varying. Then to this cyclic load or varying load, and during that time speed remain constant. Suppose when lift goes from first floor to second floor, 5 persons inside the lift, and it rotates at some rpm. Again at this second to third floor, 6 persons, load is going to vary and speed is also going to vary. In this way you can talk about that. So how to select the bearing for that? For when the ball bearings are subjected to a cyclic or a load or a speed, then what is the question? How to find out the dynamic load? And why dynamic load? You know very well. To select the bearing from manufacturer's catalog, we have to find out the dynamic load. And once you have a dynamic load, you can easily select the bearing from manufacturer's catalog. Then the condition is cyclic load and speeds. So how to find out this dynamic load, that we are going to see here. It's very simple one. So what we have to do, we have to consider the complete work cycle. Now here, instead of explaining here, I would like to show again one figure. It's a varying load condition figure. Look at this. Now I have considered from up to this end. This is the complete one work cycle. Now this work cycle is divided into three elements. This is element 1, this is element 2, and this is element 3. And again here this is the case of varying load case. In element 1 also load is varying, element 2 load is varying, element 3 load is varying. Try to understand. But here to find out the dynamic load, we have to consider complete work cycle. This is one thing. We have to complete one work cycle. Work cycle means after that again it repeats. It starts from this again. This is second cycle, third cycle. It is happening. That's why we have to consider the work cycle. Now again, what we have to do? We have to divide this work cycle into different elements. Suppose now I have shown here three elements. If you would like to consider X elements, you can say towards this size element X. And this element 1, suppose the constant load, here it is not constant, it is varying. Assume just to have to derive the expression, suppose this element 1 is subjected to load P1, element 2 is subjected to load P2. That means here this load P1 remain constant up to this element 1. Here this P2 remain constant, and then here P3 remain constant for element 3. And again, during that time, the speed of during this element 1, what is the speed here when P1 load is acting? It rotates at N1 RPM. When load P2 acts on it, that time it rotates at N2 RPM. And when load P3 acts on it, it rotates at N3. That is cyclic load and cyclic speeds. It's okay. Then, but this element 1, when load P1 is acting and rotates at N1, during that time, the total out of this work cycle, suppose it's N. The N1 is the revolution completed by this load P1. Similarly, N2 revolutions are completed by this element 2, P2, and N3 revolution by 3. And total revolution of this work cycle, N is equal to N1 plus N2 plus N3. So you can say it's a complete work cycle. Now what we have to do? The same thing I have written on earlier slide here. I am going to discuss these things with you. The first, what you have to do? You have to consider the complete work cycle. Whatever may be the number of elements, it may be X elements. Okay, X. Then find out the dynamic load capacity of the bearing, that we will do, and then divide the work cycle into number of elements that I have already told. Now suppose assume work cycle is divided into X element. So how much? So you can suppose take the load P1, P2, Px be the load which is acting for different elements x1 to up to xn, suppose n number of elements. Then n1, n2, nx be the speed during these elements. N1 speed when P1 is acting, N2 speed when P2 acting, nx speed when Px is acting on it. Okay, in this way you can do the analysis. Now what we have to do, suppose we have considered the x elements and P1, P2 be the loads during that elements, and N1, N2 be the speeds. Now we know very well load life relationship. Suppose for first element, what is the load life relation? L is equal to C upon P raised to 3 into 10 raised to 6 revolution. Okay, now here 3 already, why it is used is for the ball bearing, that's why it is written. This is the load life relationship, we know very well. Now suppose for first element, what is the life consumed due to the load P1? You can assume a life L1 is corresponds to the load P1. Similarly, life L2 corresponds to the load P2, and L3 lives correspond to load P3. That means for element 1 or first element, life L1 corresponds to load P1. So we know load life relationship here. So we can substitute here. What is the load life relationship? L is equal to C upon P raised to, and here 1 by P or is equal to 3 or 3 by, the 10 by 3 for the roller bearing. That's why this equation is written. So what we have to do? It's a element 1. That's why suffix 1 is for the L, and load P1 suffix is used here. This is the, but we know that In a one revolution, how much is the life consumed by this element 1? This is 1 upon L1. 1 upon L1. Similarly, life consumed by the L2, the element 2, that is 1 by L2. And you can add it based on the number of elements, or you have divided that work cycle into different. Now, again, what we have to do? In one revolution, life consumed is 1 by L1. So what is the value of L1 from load life relationship? This value. You can substitute this value here. Here, L1. So 1 upon L1 means here you have to substitute this L1 is equal to this value. So what you will get? Look at this. Once again, I will repeat. This is the L1. But like in one revolution, line consumed is equal to 1 upon L1 for element 1. So you can substitute this L1 here. So what you will get? This expression. You can check it. P1 cube by C cube into 1 upon 10 raised to 6. Okay. Then what you have to do? This is for element 1. I have told element 1, 2, 3 for subjected to load P1, P2, P3, and how much is the revolution during that time, that is N1, N2 and N3, and speed it rotates at N1, small N2, small N3 RPM. Okay. Then similarly, you can write down here the life consumed by the second element N2 for N2 revolution. As I have stated, the same, the for first one from load life relation, how much is the life consumed by the element 1? You have got this expression. Similarly, you can write this expression to N2 into P2 cube upon 10 raised to 6 into C. And similarly, you can write for element 3 and 3 P3 cube upon 10 raised to 6 upon C cube. Similarly, you can write Nx into Px cube upon 10 raised to 6 into C cube. Okay. This is for different elements. Then what you have to do? You have to add all these life consumed here. You have to make the addition as per your number of elements. So here adding this N1 P1 raised to cube upon 10 raised to 6 into C cube plus for this element 2 plus dash dash for X element it is written. Adding these elements, you will get the life consumed by. And when we have to write this statement for a life consumed by the complete work cycle, so what we have to do? P1, P2, P3 are acting, and you know very well, to find out the dynamic load, first we have to calculate the equivalent load. If that's why the analysis, how we are changing the analysis, look at it. If P is the equivalent dynamic load for the complete work cycle, then life consumed by the work cycle is given. So what you have to do here, we have written for this is element 2, this is for element 1. So similarly for complete work cycle and load equivalent dynamic load, complete work cycle total number of revolution is capital N into what is load? Equivalent dynamic load or equivalent load is P upon 10 raised to 6 into C cube. This is for complete work cycle. So what you have to do? Adding all these elements, life consumed by each elements, you have this equation A, and for complete work cycle, you have this equation B, and this is equation A. So you can equate these two equations for different elements you have added, and here this is for the complete work cycle. After equating, what you will get here? Let us see. I am going to write is equal to here directly N into Pe raised to cube upon 10 raised to 6 into C cube. Now here a common term, you can take common from all these terms and it gets cancelled here. Then what is remaining with you? N1 into P1 cube. Look at this, I have written here. Then into P2 cube, here it is written plus dash dash. This term is equal to N into Pu cube. This term is written. But you know very well what is capital N? N is equal to N1 plus N2 plus Nx. X is the number of elements. Try to understand. So again, we will modify this expression. What you will get here? The capital N is equal to N1 plus N2 plus N3. And you modifying this and rearranging the term. Look at this once again. I will show you this equation here. Look at this. This is the expression. So you can take N1 plus N2 plus N3 is equal to N. You can set any one of the sides here. Okay, so what is going to happen? And generally for a complete cycle, you can sometimes, if it is mentioned, you can take is equal to 1 also. Okay, in some of the cases, while solving the problem, you have to take the care. Now, so what you have to do, the same expression rearrange here. Look at this. The P is equal to, because of the cubic terms, the cube under root here, so you will get n1 into p1 plus n2 into p2 plus upon n1 plus n2. And this term again is nothing but a n, is nothing but a n. So that's why again you can modify this term. P is equal to 3 under root summation of n into p. Here the value of, the depends on the number of elements, the n1 p1 plus into summation. That's why term is written. So this expression which is derived here, this expression you can use to calculate the dynamic load capacity of bearing for a cyclic and different speeds. The P1, P2, P3 are the load which is acting during that element. N1, N2, N3 are the revolutions of that element. Capital N is the total work cycle, and P is the equivalent dynamic load. And once you will get the P means equivalent dynamic load. And what you have to do, the load life relation, C, P, C, L, this relation in terms of ball bearing or roller bearing. So you can use and find out the C dynamic load capacity and select the bearing from the manufacturer's catalog. Same procedure. Only here, these fundamentals you have to use to find out the dynamic load capacity of the bearing. But as I have told, in some of the cases, suppose these are the 3, 4 elements and this is the one complete cycle. You can consider this is one cycle, this is second cycle, this is third one, and this is fourth one, like this. The year load is, suppose here P1 is equal to 2. Again it goes down, here it becomes 0, then again it is going to vary. That means this case is the varying load condition. And when load does not vary in steps and constant magnitude, that means it varies continuously. It varies continuously with respect to time. That time, which equation is suitable? So now what you have to do, you have to use this equation. Again, this equation is modified here. When load is varying continuously or varies continuously, that time P is equal to integration 0 to n means uh, up to complete work cycle, p raised to cube into dn. Dn means, so that's why here why dn is considered when it is, suppose consider only one cycle here. This is one element of the cycle. A load is varying. That's why dn is taken. That means we have to take the care of in small parts, in which revolution, how much is the load which is acting. That's why it is integrated by 0 to n. Try to understand. And the overall integration gives the complete result of that. The varying load condition, you have to do this, you have to use this equation and you have to integrate this term to get the good results. And again it may be written again here, this is here n, the if it's for a cycle is taken out and it is written in this way also. You can do this. What is the integration of this considering the 0 to n limit 1 by n, you will get this expression. These expressions are used when load is varying, and this equation used when there are 4, 5 elements, but your load is 5 kilonewton, 3 kilonewton, 4 kilonewton during that works part of the work cycle, we can say. Okay, this is about the cyclic load. Now we will see one simple problems to have some more feel. Look at this here. I have taken this problem from Vivandari's book. Look at this. I am going to read this problem. Single dip groove ball bearing subjected to a, you have to always read problem statement carefully, subjected 30-second work cycle. 30-second work cycle, it's not a 1 minute cycle or a 1 minute 60 seconds, very well. 30 seconds, that consists of following two parts. That means this work cycle is divided into two part. Duration, first 10-second duration, radial load which is acting on the bearing 45 kilonewton, axial load acting on the bearing 12.5 kilonewton, and during that time speed is 720. And then out of this 30, next 20 second, radial load acting on the bearing 15 kilonewton, axial load acting 6.25 kilonewton, and speed is 1440 rpm. Static and dynamic load capacities of the bearing are, static and dynamic C is also given. C means dynamic load capacity 68, and static means CO is also given 50 kilonewton. Calculate expected life of bearing in hours. So here L and H, that we have to find out how much. But now if we are going to compare the earlier, the concept with this problem. Now here two, look at this here. This is two cycles. How much is the year N, element 1, element 2, and how much is the time which is taken by this element 1 is the 10-second time, and here it's a 20-second time, and here radial load which acts the 45 kilonewton and axial load 12.5 kilonewton during this cycle. And this cycle it is going to vary 15 and 6.25. Try to understand. And during this time, speed of this the bearing is 720 rpm, and during this time 1440 rpm. And this cycle is completed within 30 seconds here. So we have to, from this 30-second cycle, we have to find out the rpm also, or revolutions also, to get the value or to calculate the value of dynamic load capacity. Now let us see how to solve such a problem. Now what we have to do in the problem statement, first of all write down the given data. CO 50 kilonewton, dynamic load capacity 68. We know how to find out the equivalent dynamic load for a complete work cycle. This formula, P is equal to under root cube N1 P1 Q plus dash dash dash. Now in this case, how many cycles? 2 cycles. Now first our target to find out the equivalent dynamic load. Once you have equivalent dynamic load, then you can use a load life relationship and find out the dynamic load. And once you have a dynamic load, you can easily select the bearing. And once you have equivalent dynamic load, even though you can use load life relationship to find out the life in hours also. Okay. Now take the part one. Now for part one, what is given axial load? Look at this. 12.5 and radial load 45 kilonewton. And you know very well how to select the bearing from the catalog. To you find out the x and y, that is the radial and thrust factor. We have to always consider these two ratios. Last time we have discussed these things. The first ratio FA by FR and second FA by CO. The FA by FR is given in the for first, how much? 10-second cycle for part 1. Okay, 10-second cycle. The FA is given 12.5 FR 45. You will get this ratio. This FA by CO 12.5. Here it is given, and CO is equal to 50 kilonewton. This. And once you have FA by CO, you have to refer this table. I have already told. So what you have to do? FA by CO, how much? 0.25. In first column, it is given 0.25. You can select this row. Again, second thing, what you have to do? If you have selected this row, at the end or the last column, you know the E. The E is equal to 0.37. But what we have to do, FA by FR here, whether it is greater than E or less than E. So look at this. This 0.37 is greater than this calculated FA by FR. So you can say FA by FR is less than E. FA by FR, this is FA by FR, 0.287 is less than this E, FA by FR. That's why I am going to select this column. FA by FR is less than E. And in this column, we have to come where FA by CO is equal to 0.25. You can select this is X and this is Y is equal to 0. Now you have X and Y. So what you have to do? X is equal to 1, Y is equal to 0. So you know very well dynamic load. EP is equal to, so what you have to do? So you will get P1 is equal to FR is equal to 45,000 Newton. What is the value? P1. This P1 we are going to use here to find out the equivalent dynamic load. Then how to find out the N1? This is very important. Number of revolution for this first element of 10 seconds. Look at this here. It rotates at how much RPM? 720 RPM. RPM you can convert into second divided by 60. So you will get RPS. But how many seconds here it is given here? The revolution per second, and the second gets cancelled. N1 you will get 120 revolution. You will get here it's 120 revolution. So we have calculated a 10 second for the first part. 720 first part where bearing rotates at 720 RPM. RPM convert into RPS, second gets cancelled, you will get revolution. In this way, N1 is calculated. Similarly, you can do the calculation for part 2 also. Look at this for part 2. For Part 2, AP by APR, AP is given 6.25 kilonewton, APR 15, you can find out this ratio. Then AP by CO 6.25 FO, you will get this. You have to check again. In the first column, AP by CO, it is 0.2125. Hai kya? This value is not available, but it lies in between 0.070, 0.130 here in between. So what you have to do, so you will get the E is near about 0.30 or 31, and FA by FR is equal to 0.17. If you are going to this E with FA by FR, so you can say 0.417 is greater than 0.30 or 0.31. That's why we have to select this column, FA by FR, this column. Selecting this column, when we comes to this point, but we don't have this value, so what you have to do to find out the value of X and Y, you have to carry out here the linear interpolation. And by using, but value of X remains same, that is 0.56. Only interpolation that you have to carry to find out the value of Y. So using the linear interpolation, you will get the value of Y, that is 1.42. You know very well how to take calculate by using linear interpolation. So once you have this X and Y, P2 is equal to X FR plus Y FA. In this case, it is not mentioned inner race rotates, outer race rotates. You can assume inner race rotates. That's why B is equal to 1. Load correction factor is not given, or load factor. That's why no need to multiply it by this P by load factor. So just assuming 1, you will get P2 is equal to this value. And N2, how to find out N2 is, this is for 20 seconds. During the element 2, it rotates at 1440 RPM. Again, RPM by 60, you will get RPS 20 second into RPS. Second cancel, you will get 480 revolution N2. So we have now P1, we have now P2, we have a N1, and we have a N2 revolution. Now what you have to do, we can easily use the equation. Look at this here. The total N, suppose N1 plus N2, you will get 124 600 revolution. But very interesting thing, I will elaborate later. The before that, first of all, find out equivalent dynamic load. Cubic root N1 into P1 cube plus N2 into P2 cube by N1 plus N2. The N1 plus N2 how much? 600. I have substituted. What is N1? You have calculated 120, N2 480, and P1 already calculated from part 1, P2 calculated from part 2. You will get the PE, or P, you can say equivalent dynamic load. It's okay. Now what we have to do? You have to calculate the bearing life in hours. So you know very well load life relationship here. L10 is equal to C upon P raised to Q. P already calculated by using this expression of cyclic load. Okay. What is C? C is also given in problem statement. So what is the main problem here? The L10 that you have to calculate. So directly you will get L10 here. The L10 in million revolutions. So you can calculate. But one interesting thing now, but it's in million revolution, you have to convert it into hours, because in question it is asking hours. How to convert it into hours? L10 H is equal to L10 into 10 raised to 6 upon 60 NH, or you know very well, L10 in million revolution is equal to 60 into N into L10H upon 10 raised to 6. I have modified this equation into this. L10H is equal to L10 in million revolution. Huh? It is in million revolution into 10 raised to 6 upon N. But what is this N? Speed. And for this purpose, give attention here what I am telling to you. Now in this problem, number of revolution in one work cycle is how much? 30 seconds. And for this 30 seconds, we have calculated number of revolution 600. Try to understand. This complete work cycle, number of revolution of for this 30-second duration is equal to 600. For 1 minute 60 seconds, how much? It's a double. The double means 1200. So what you will get? N is equal to 1200 RPM. Try to understand what I am telling. The number of revolution in one work cycle for 30 seconds is equal to 600. Which 600? This N1 plus N2. But we have to use N here, revolution per minute. We have to take into for a minute. It's for a 30-second means half. For a minute it becomes 30 plus 30. You can add 600 plus 600. 1200 RPM. The put substitute here N is equal to 1200. and then you will get the life in hours. Try to understand. This is about the problem. In this way, you have to take the care while solving the problem. This is about cyclic load and this. Then another important point which is related to bearing, a very important point is the bearing, reliability of bearing. In other terms, you can say probability of survival of the bearing. So what do you mean by reliability of the bearing? Generally, we have defined the life in terms of L10 life. What do you mean by L10 life here? The 90% of the group from the same identical bearing group which can sustain without fatigue failure, or where the first the crack or the some the uh, sign which occurs to that group, the 90% of the bearings are going to sustain, and that is L10 line. Or bearing with, that's why here in the reliability of the bearing or probability of survival of the bearing, so we are going to use, what do you mean by reliability here? Bearing with probability of survival other than 90%. Now here 90% of bearings we can sustain without fatigue failure. The rating life is the same one, 90% of group of identity bearing which will complete or exceeds the life. That is the thing. So that's based on that. Reliability is defined as it's the ratio of number of bearings which have successfully completed n million revolutions. N million revolution means, again you can define 90% of the bearing that can sustain. Try to understand number of bearings upon total number of bearings under test, that is the reliability. And that's why when we are considering the rating life and bearing of probability survival of 90% of the group in terms of rating line, that means reliability of the bearing is 0.9 or 90%. Always that is assumed. And because we are considering L10 life, that means 90% of the bearing. That's why reliability of the bearing. But in some of the cases where there may be safety point of view, reliability may be required more than 90%. That means bearing should not fail, or a group of that bearing should sustain more than that. More than 90% bearing can sustain that load in some of the application. So what to do and how to find out the reliability of the bearing which is not in 90%, maybe less or more than 90%. How to find out this reliability? For that purpose here, Mr. Weibull distribution curve that we have to use. Now here according to, we will look at this here bearing life towards this side, percentage of bearing in service. Here this is 100 bearings. Now here L10 life means 90% of the bearing can sustain or exceeds this, the without fatigue failure, you can say. You say L10 life. I have written L50. The 50% of the bearing can sustain. That's why life L50. In this way, you can write here. L40 means 60% of the bearing. Here I L40. Okay, 60% of the bearing in this way. But here, the if you would like to find out the reliability other than 90%, then we have to go for a Weibull distribution. And this Weibull distribution or a curve is a statistical curve. It gives the relationship between bearing life towards x-axis and reliability. Try to understand how much percentage it is going to sustain or percentage of bearing in service by the relationship between bearing life and reliability is given by Weibull distribution. And according to this statistical, the curve here, the equation, according to this Weibull, R is equal to E raised to minus L by A into B. Now here, I will check it this equation, L by A raised to B. L by A raised to B here. It's not multiplied by B. It's a L by, try to understand here. R is equal to, once again I will write E raised to, sorry, R is equal to E raised to minus in bracket L by A raised to B. This is the expression. This is the expression. Okay. Now, where R is the reliability in fraction, L corresponding to life and AB are constants. We will see how to, what are the values of this constant. Then this equation you can rewrite, Weibull equation, rewriting 1 by R is equal to E raised to LA by A raised to B. Again, you can take the log, you will get log to the base e, because here a exponential term. The log to the base e 1 by r is equal to L by a raised to b. This is, you can say, equation number 1, no problem. And where you know the AR, yeah, you can, if you would like to modify the same equation for 90% of the bearing that is going to sustain, that means for L10 life, what you have to do here, you log to the base E 1 upon reliability. How much for L10 life means R90 is equal to L by A raised to, how much is the year life? L10. Here this equation is modified here. L10 is the life corresponding to reliability of 90%. That's why L10 is written, and here reliability 90%. Try to understand. So this equation is modified. There are two equations now. This is one equation and this is second equation. So you can take the ratio of L upon L10. This is L and this is L10. From the same equation A and B, the L upon L10 is equal to log to the base E 1 upon R, log to the base E 1 upon R90 raised to 1 by E. So taking the ratio of L upon L means from L is equal to, and this is L10. You, from equation A and B, you will get this expression. You can do it, no problem. So you will get this expression, and this expression is used, I have highlighted one point, when reliability is one other than 90%. Now suppose someone is going to ask you find out the reliability of 80%. So you can write here, you know, the R 80 that you have to find out, and the life, from reliability of 80 you can find out the life, or for the life you can find out the reliability of this R gives this value. Try to understand. And L10 and R90 remain same, only this L and R that you have to find out. That's why here it is written, it is used for selecting the bearing when reliability is over than more is other than 90%. But here the constants are given. Va is equal to, suppose you would like to use Webel distribution, A is equal to 6.48, 6.84, B is equal to 1.17. And again, this value of A and B are based on L50 is equal to 5 times the L10. It's okay. You know the L50 life means median life, 50% of the bearing can complete or exits. It's okay. By using this expression, you can find out the reliability of the bearings other than 90%. Try to understand. Then next thing, suppose someone is going to ask you find out the reliability at 95%. So you have to find out this. It remains same. So for 95%, these two parameters plays important role. Accordingly, you can solve and do the calculations. Okay. Then next one. Sometimes what is happening? There is one system. It consists of a some number of n number of bearings having the same reliability. Then how to find out the reliability of such a complete system? To find out the there is one system. It consists of n bearing having same reliability. The reliability of this complete system is given by Rs is equal to R raised to n, where R is the reliability of each bearing, n means number of bearing in the system, and Rs is the system reliability. Rs is the system reliability. Try to understand. Now here, this RS means system reliability means probability of one out of n bearing failing during in its lifetime. So in this way, this is the reliability or probability of survival of the bearing. So you should know that. Remember this equation, Webel's equation, and how to derive this equation. It will help you. And in some of the books, after substituting the value of A and B, if you are going to substitute this value, you will get some terms here, some constants here. So in some of the data books, you will find this equation may going to vary after substituting the value of A and B also. It's okay, but the logic, fundamental logic is same. Values are also same, so you can use it this. And how to find out the system reliability? So you can use this expression, R is equal to R in raised to n. N means number of bearing in the system, and R means reliability of that bearing or each bearing, which is called. This is about the today's session. Thank you. I have referred this book, Vivandari's book, for this the session. Thank you.